presentation. I am a PhD candidate from China, Northwestern Polytechnic University. The topic of my presentation is a simple and efficient X FEM approach for non-analytic propagation. You know, the fatigue failure is one of the main failure forms of structures, and the geometry of cracks is most time is complex in most situations. And take this picture as an example. We can see the dark part. The dark part is the fatigue fracture, and we can see the crack surface is non-planar and the crack front is irregular. It is difficult to work out an analytical result for such problems. So, a flexible and efficient numerical method for three-dimensional crack problem is needed. The extended finite element method is originally proposed by Professor Pacheco and Black in 1999. It is capable to model moving discontinuous by adapting enrichments to the standard finite element approximation field. And this benefit makes it a good choice for the fracture problem. Our purpose is to work out a numerical approach for three-dimensional fracture problem based on the X FEM method. And my presentation will be divided into 4 parts. First, I will introduce the characterization of the crack geometry. The level set method have been proved to be a good supplementation to the X FEM method, and as one can perform computation, involve codes and surfaces on a fixed mesh. In the level set method, a crack can be described by 2 level set functions, one for the crack surface and another for the crack front. We can call them the surface and the front level set functions. And to initialize the level set values for a given point, we need to locate the closest point on the extended crack surface and the tangent surface across the crack front. And then the 2 level sets can be calculated using the 2 expressions. If for the analytical surface, the initialization step is easy, but if the initial crack is in complex shape, the initialization step will be difficult. To solve this problem, we adopt a triangulation scheme introduced in this paper. Arbitrarily shaped crack surface can be divided into the flat triangles and extended to the entire domain along the extension vectors. And then the outline of the polyhedron will become the crack front, and the points on the crack front will be chosen as the source points for crack growth. As it is not smooth on the vertex of these triangles, so the normal vectors are chosen as the weighted average of those on the surrounding triangles. After that, we define three distance functions to the discrete crack surface. There are distance functions to the crack surface and crack front, and to the extended crack surface. And the lines in the 3 colors are the isolines of the 3 distance functions. After that, we can calculate the 2 level set functions according to the geometrical relationship of the 3 distance functions. And These are the result of the level set result of correct initiation. Next, I will introduce the X FEM approximation for virtual problem. This is a well-known displacement approximation for the fractal problem. Here the H is the Heaviside enrichment function, which is constant on each side of the Planck surface. And phi is the enrichment functions to simulate the asymptotic field surround near the Planck front. And R and theta is defined in the local system. The definition of the enrichment sets can be based on the nodal values of level set functions. These two are the criterion for finding whether an element is enriched, which means if an element is intersected with the Planck front, it will be deeply enriched, and if an element is fully cut by the Planck surface, it will be sharply enriched. Then the set of enrichment nodes are defined based on the element enrichment type. Something wrong with the equations. These are the element contributions to the finite element equations. And here is a brief introduction to the integration scheme for the enriched elements. If the element is cut by the Planck surface, it will be divided into sub-elements, both above and below the Planck surface, and the four-node Gauss procedure is adopted to each sub-element. And for the blending elements, higher-order Gauss procedure is used. And we can talk about the update of Planck surface. In our work, the stress intensity factors are chosen as the driving forces for Planck growth, and they are calculated using an interaction energy integral method. And this is the expression of the integral, and the superscript ox means the auxiliary field, and the integral domain is a tubular volume around a segment of Planck front. By introducing an appropriate form of auxiliary field, we can relate the integral to the mixed mode stress intensity factors. And then the Planck increments are first calculated on the source points. The Planck growth angle is calculated based on the values of mod 1 and mod 2 stress intensity factors, and the parasol is adopted as the fatigue Planck growth model. We can use it both in an N-dominant form and K-dominant form. And for the source points which would be growth outside the model, it will be replaced by its projections on the boundary. And if the front segment would be too long after the propagation, the midpoint of it will be chosen as a new source point in order to maintain a good shape in the next propagation. Here is a little problem to this. The source points are defined on the explicit Planck front, but the stress intensity factors are calculated from the results of the implicit Planck front. So there's a problem in such kind of element. For this element, we first locate the projection of source point on the implicit Planck front, and this is the offset. And in another side of view, the black line is offset, and the blue line is the calculated Planck increment. So using this triangle, we finally choose the red line as the actual Prague increment on the active soft points. So we give two simple examples. The method introduced before is implemented in objects. There are three user subroutines are used. First, consider a crack initiated from a dim hole. This is the model size, and here follows the material contents. We simply update the crack every 10,000 stress cycles. Here is a message stress in step 8, and the fatigue failure happens after 12 steps of simulation, and this is the final shape of the crack surface. And next example is an inclined penny-shaped crack in a cube. And this is the angle and the size of the initial crack and the size of this model. The crack growth is controlled by the predominant form Paris law, and the maximum crack increment on the soft points are supposed to be 0.1 meter. This is the crack surface of 9 steps of propagation, and the right one is the crack sizes in each step. Here come some conclusions. We propose an X FEM numerical approach covering with the hybrid, explicit, implicit crack description. And the correction process is adopted to eliminate the offset between the two crack fronts. And both examples for planar and non-planar crack problems are presented. And the two examples seems too simple, and it's a kind of verification problem examples. So maybe in the following work, the method presented here should be applied to more practical problems. Thank you for your attention.